In our project, we have handled the third problem in the project handout, which is sentiment analysis, which is a binary classification task. We analyze the performance of different neural network architectures, including sequential models, CNNs, and transformers. For evaluation, we use two datasets, Twitter and the IMDb dataset, which are benchmark datasets for sentiment analysis. We additionally also address the problem of multiple domain adaptation of neural networks and dealing with small datasets in the natural language processing space.
Let's have a look at some of the sequential models that we have considered. The first sequential-based model is the recurrent neural network, also termed as RNN. This model helps us to consider the sequence of the input data, which cannot be processed by a normal feed-forward network. These models are slightly inefficient compared to models such as CNN, as values at each time step is required by the next time step. Because of this, the computations cannot be parallelized, and hence these take more time than other models for training. Here, you can see the model architecture which we have considered for our experiments. It consists of an embedding layer followed by a dense layer, and finally a dense neuron which acts as our output with the sigmoid activation function. We have also experimented with gated recurrent units, which are an enhancement to the RNN layers with the addition of two gates, namely reset and update gate. These gates help us to retain information in longer chains of sequences. Next, we have LSTMs, which is further a more complex network with two more gates, namely forget and output gate. These four gates in the LSTM layer helps us to retain information in longer chains of sequence. Lastly, we have the bidirectional LSTM layer, which consists of an additional LSTM layer, which is trained on the reverse copy of the input sequence and helps to gather more sequential context. Now, let's have a look at some of the key findings from our experiments. We can see that GRU and LSTM layers perform significantly better than RNN due to their ability to capture long-term dependencies. GRU performs a tad bit faster than LSTM, which is expected as LSTMs have a more complex operation with their four gates. GRU performs better than LSTM in the IMDb dataset, but vice versa in Twitter dataset. This is due to the fact that LSTMs perform better when there is a huge number of data points due to its complex structure, while GRU performs better efficiently in smaller datasets. Lastly, the bidirectional LSTM performs better for Twitter dataset due to the fact that the huge number of trainable parameters in the model overfits on the small number of training samples in the IMDb dataset. But on the other hand, it provides better results with the huge number of training examples in Twitter dataset.
Now, let us take a look at our second approach of using convolutional neural networks. Now, let us take a look at convolutional neural networks as our NLP model structure. CNNs are typically used for computer vision tasks. However, findings by many authors prove that CNNs can be used for tasks in natural language processing and showed promising results. In our case, the model architecture consists of three 1D convolutional layers followed by max pooling and then three fully connected layers for the sentiment analysis. The CNN model gives worse performance than all the other models since it is unable to capture the long-term sequential dependencies in the text sequences. However, it is noteworthy that the model gives a reasonable performance on both the datasets and it takes around 15 minutes to train on the Twitter dataset. As visible from the results, a big advantage of CNN-based NLP models is that their training and inference times are very low. Due to the shared weight architecture of convolutions and their filters, the number of parameters required to learn significantly reduces.
Let's have a look at the transformer architecture with the example of the BERT model. The BERT model is made up of the encoder layers of the transformer architecture along with the attention mechanism. It requires some input preprocessing, such as the tokenization of the sentence and adding a CLS token in the beginning. It outputs embeddings in the form of a pooled embedding, which correspond to the embedding of the entire sentence, and also the token-wise embeddings. Looking at the model architecture, we have the input layer, the preprocessing layer, which is taken from TensorFlow Hub, which pre-processes the input sentences before feeding it to the BERT layer, the BERT encoder layer, which is again taken from TensorFlow Hub, to output the BERT embeddings. For the sake of our task, we use the pooled embeddings. And it is followed by a fully connected layer with dropout and a single neuron for binary classification of sentiment. Analyzing the results, we see that BERT offers almost state-of-the-art results on both the dataset. The BERT-based models offers an accuracy of 82.47% on the Twitter dataset and 88.4% on the IMDb dataset, which is much higher than the BERT small model. However, the BERT small model is much faster in terms of the training and the inference time. This is mainly because the BERT-based model has much more parameters than the BERT small model. Analyzing the results on the Twitter dataset across architectures, we see the BERT base model offers the best accuracy, but takes an unreasonably long training and inference time. The CNN model offers the worst accuracy, but is very fast. The bidirectional LSTM offers a result comparable to BERT, but takes a reasonable train time. On the IMDb dataset, BERT again offers the best accuracy in a reasonable train and inference time. CNN also offers a good accuracy and is extremely fast, which makes it really good for real-time inference tasks. GRU model, which is a sequential model, is better and faster than the BERT small model.
The second aspect we have studied is to deal with domain adaptation. Generally, well-known pre-trained word embeddings like BERT tend to perform well on nearly all types of domains. This is due to a variety of factors such as a large corpus and generation of embeddings in a context-dependent manner. Although word embeddings work relatively well on different domains, the performance of these models drop if they are used on very niche domains. There are two approaches to deal with domain adaptation. The first one is hyperparameter tuning. Fine-tuning is done in a few ways. Firstly, a few layers of the model is freezed and trained on the target text corpus. Secondly, another method is tuning the number of word embedding dimensions to fit the target domain, which can also be beneficial. The second approach is using domain-specific data. This has been done in word-to-vec embeddings. Word vectors for bioinformatics, known as biovectors, are used in DNA, RNA, and protein studies. The limitation of this method is that it is very expensive to obtain domain-specific corpus since it is not commonly available on the internet.
Let's have a look at the issue of dealing with small datasets. The first approach that we have considered is called back translation. In this technique, we convert a sentence from English representation to a second language and then back to English. In this way, we can have a sentence with a slightly different structure, but with the same meaning. For our use case, we use the pre-trained tokenizers and model from the Transformers library and have converted the English reviews in the IMDb dataset to German, as you can see in the image below. These German sentences were then translated again back to English and added to our training samples. The next technique we have used is called word replacement. In this technique, we randomly pick a word and replace it by its synonym or any other word as deemed fit by the model, which gathers the context of the sentence. In the example below, we can see that rented this movie gets replaced by saw this movie, which again has the same meaning when we consider the whole sentence. For the third technique, we insert multiple words in the already existing sentence. For this, we use pre-trained models which are able to insert words appropriately by judging the sentence context. For our last approach, we use pre-trained models such as BERT, which have already been trained on a large set of corpus. Because of this, the model doesn't require the whole training dataset, and even with a small fraction of the dataset, the model gives us comparable accuracy, as you can see in the table here. I would like to conclude by saying that through our multiple experiments with various neural network architectures, we were able to learn the practical usage of the theory taught in this course. We could achieve significantly close to state-of-the-art results for both our dataset, even after considering that we were implementing similar models due to the constraint of computing resources. Lastly, researching on the topics regarding domain adaptation and dealing with small datasets opened us to a whole new aspect of NLP related tasks, and we got an opportunity to implement some of these techniques as well. Thank you.